The Reimer-Tiemann reaction is a classic organic synthesis method used to convert phenol into salicylaldehyde. This process introduces an aldehyde group specifically at the ortho position of the aromatic ring, providing a pathway to synthesize important precursors for pharmaceuticals and fragrances. Understanding this mechanism is vital because it demonstrates how a neutral molecule can be transformed into a reactive intermediate. The final product, salicylaldehyde, is a key building block for producing aspirin and various flavoring agents used globally in the chemical industry. The heart of this reaction is not the chloroform itself, but a highly reactive species called dichlorocarbene. This electron-deficient intermediate is generated in situ and acts as the electrophile that attacks the electron-rich phenol ring. First, a strong base like potassium hydroxide deprotonates chloroform. The resulting carbanion quickly loses a chloride ion through alpha elimination. This creates dichlorocarbene, a neutral carbon atom with only 6 valence electrons and a vacant p orbital. Simultaneously, the base deprotonates phenol to form the phenoxide ion. This ion is much more reactive than neutral phenol because the negative charge on oxygen is delocalized into the benzene ring, increasing the electron density at the ortho and para positions. The nucleophilic orthocarbon of the phenoxide ion attacks the electrophilic dichlorocarbene. This step breaks the aromaticity of the ring temporarily, forming a non-aromatic intermediate with a dichloromethyl group attached to the ortho position. To regain the stability of the aromatic system, a proton is removed from the orthocarbon. The electrons from the CH bond flow back into the ring, restoring the conjugated pi system and resulting in a substituted phenoxide intermediate. The dichloromethyl group now undergoes alkaline hydrolysis. 2 hydroxide ions replace the 2 chlorine atoms through nucleophilic substitution, leading to an unstable geminal diol intermediate on the side chain. Geminal diols are typically unstable and spontaneously lose a molecule of water. This dehydration step converts the side chain into a formyl group, effectively turning the intermediate into the phenoxide of salicylaldehyde. In the final step, the mixture is acidified. The phenoxide oxygen picks up a proton to regenerate the hydroxyl group. The final result is salicylaldehyde, characterized by its distinct almond-like odor and ortho-substituted structure. Let's apply this to low-cresol. Since one ortho position is blocked by a methyl group, the formyl group will attack the other available ortho position, demonstrating that the mechanism remains consistent even with substituted phenols. In the case of 2-naphthol, the reaction occurs at the 1 position. This follows the same logic of attacking the most nucleophilic site that allows for the stabilization of the intermediate complex before restoring aromaticity. The reaction is typically carried out at 60 to 70 degrees Celsius. While highly specific, yields are often moderate due to the formation of some para-product and potential resinous side products from the high alkalinity. To summarize, the base generates dichlorocarbene, which attacks the phenoxide ion. After restoring aromaticity, the dichloromethyl group is hydrolyzed and dehydrated to form the aldehyde, followed by final protonation to yield the product. Before we finish, test your knowledge. What is the actual electrophile that attacks the benzene ring in this reaction? Is it chloroform, the dichlorocarbene intermediate, or the hydroxide ion? The correct answer is B, dichlorocarbene. Its vacant orbital makes it highly electrophilic toward the phenoxide ring. Mastering this mechanism provides deep insight into carbene chemistry and aromatic substitution. Thank you for watching. Generated by Vision Solve AI.